Fantastic. Good morning, everyone. Appreciate you all coming to listen to this very exciting panel. One of many, it's been a great conference already, and I think this panel brings forth some of the importance that a lot of us, we're working through geothermal projects, thermal energy network projects. In many cases, we're so focused on thermal side of these projects that we lose sight of the other obvious component, right? It's a major and very important component. The electrical side of this is very important to the development, right? We have to make sure that as we're building these systems out, doing it in the most effective, efficient ways as we can, reducing the overall burden on grid and our infrastructure, many times campus settings. These systems can grow to massive scale and have a really big impact. So all of that said, these folks here are have put together a great line of presentations to help kind of drive to, how to drive down those grid impacts at building level as a building block to build up at scale. So with all that said, I'm going to pass over to Jeff, and we're going to get started promptly.
Thank you. Well, it's very good. Hey, whoa.
Thank you, Mitch.
Thank
you. To make sure our cards are switched. Can't start, right? All right, good afternoon. This is one of my favorite subjects. We talk about ground source heat pump systems, and the system isn't just the heat pump. So pump sizing has a big impact on the operation of the system, but it also can affect the grid and system efficiency, and that's what we're all about. In Bob's presentation previously, he had some really good examples of grid impact, and so I want to build on that when we talk about pump sizing. So, you would think the pump in the system is a pretty small kW demand, kilowatt hours of the total system. You have the heat pump and all the various associated electrical usage, and that is true with proper design of the piping system. The piping system obviously is pretty important for a ground source heat pump. Also, if you're using variable speed pumping versus constant speed pumping, and what type of antifreeze, concentration, all those are factors which certainly can make it a very small percentage of kW demand and also kilowatt hour usage. But unfortunately, in my 39 years now in the industry, I've seen too many that didn't consider some of these things: system pressure drop, piping design, large constant speed pumps, and I could go on, but that's a pretty big factor when we're looking at the total system. It's not just about the heat pump efficiencies. So I have an example here from Illinois. Do as we say, not as we do, right? So this is a small commercial job, about 56 tons. It had 14 heat pumps between 2 and 6 tons in capacity. And unfortunately, they sized this with 3 5-horsepower pumps running 24 hours a day. So 15 horsepower of pumps for 56 tons of equipment. They had 10.5 kW demand just for the pumps. So if you had less than 13 tons operating, the pumps actually were higher demand than the heat pumps. And that's never really a good situation when you're looking at a system that you want to see efficiently as possible, but also you want to lessen the grid impact. So this particular job was a retrofit. They replaced these constant speed pumps running 24 hours a day with variable speed circulators. These were wet rotor circulators and dual heads. So they could run with one pump or both pumps at 2.6 kW demand maximum. So if it was running full out with both pumps, 2.6 kW versus 10.5, and they were also changing pump speed based upon the number of units running. So the graph over here on the right, you can see even if all the units were running and the pump was maxed out, you're looking at about 2.6 kW versus 10.5 kW. But if only one heat pump was running, in this example, it shows a 3.5 ton, it's running at 100 watts instead of 10.5 kW. So you can see here, you would expect the pump to have a very little impact on the total system kW and kilowatt hours. In this case, it's wasn't the case, at least originally, until it was replaced. So we have a lot of resources, fortunately, to size these properly. I pulled up ASHRAE 90.1, which is really important for commercial applications. It's specified in a lot of building codes and municipal requirements. There's a clause here I just pulled out of the 2022 edition of 90.1, and this actually requires variable speed control for systems with 5 horsepower or larger pumps. So you have to actually control that pumping if you want to meet 90.1. And no more than 30% of the design wattage at 50% of design water flow. What that does is make sure that when part load, we're adjusting the pump speed. We're not just running full out, and we're also controlling it. So that's right out of 90.1. That's a great resource as backup if you do have those conversations. This blue book, we call it in the industry, it's the ASHRAE design book. I keep it on my desktop, so that tells you how much I refer to it. This is Kavanaugh and Rafferty, or the authors here, and it's quite a useful resource. It not only gives you some power benchmarks for pump sizing, but it also talks about the impact of pump power, and it provides some examples. Plus, that's tied into piping fundamentals, pressure drop calculations, and it explains the different types of pumps. So this is a great resource. If you don't have it, it's available through the ASHRAE bookstore, and it's actually the basis for IGSHPA's design courses on commercial designer workshops. So this is something that if you don't have, it's a great resource. I'm using it for pumping at this moment, but it also talks about ground loop sizing and so forth. One of my favorite charts in that book is on pump power benchmarks. I added the green text here just so we could look at watts per GPM. If you remember that example I had in Illinois, it was way up there with the original pumping. With the replacement of those variable speed circulators, it was down to 15.4 watts per GPM. So even a retrofit would have qualified for a grade A. Nobody wants an F, right? So we want to strive for grade A. This chart I use all the time. It not only gives you guidance on watts per ton, horsepower per ton, but even if you're doing the pipe sizing, you have some available head in that last column. You want to stay below 46 foot of head for that pressure drop calculation. So this is a great resource if you're looking at pump sizing. Another resource is the C448 standard. This is a design and installation standard, binational, US and Canada. There's a brand new edition coming out next month in May. And this provides minimum requirements for the ground heat exchanger, your piping system, heat transfer fluid, heat pump selection, flushing, purging, testing, and startup. And all of those affect pump performance. So if we're just looking at pumps, which is what my conversation is today, this is going to also help with guidance. So the ASHRAE 90.1, the ASHRAE Blue Book, the standard, if you look at that, that's going to provide minimum requirements, and it's pretty easy to get it to an A grade on that pump sizing. We can choose different configurations, obviously, depending upon the system, the size. Is it light commercial? Is it heavy commercial? So based upon how the piping is designed, how the heat pump placement is, are these small packaged units, is it a central system? A lot of different choices here with central pumping. Primary, secondary is becoming very popular. You might have a variable speed circulator on the ground heat exchanger and individual pumps at each of the heat pumps. So now you're controlling the ground heat exchanger flow rate based upon temperature, and the heat pumps are being controlled based upon whether that heat pump is operating or not. So I won't get into a lot of detail, but there are just many options here when it comes to selecting those pumps. So just in summary, since we have a number of speakers here, I'll wrap up with my summary, and then we'll have some time for questions. Really, the pumping should be a very small percentage of your overall system peak demand and your total kilowatt hour usage, if designed properly. A lot of resources available, not only the resources I mentioned, but training from IGSHPA and other organizations are available. We should really try to use variable speed pumping when possible. Technology is to the point now where it's very inexpensive. It's easy to design, not to mention the controls that are available make it much easier to monitor. A lot of the variable speed pumping even come built in with, say, back net controls and things like that. So it's changed even in the last 10 years on availability. Improper design is problematic. So if we want to get back to that Illinois example, which we don't, proper pump selection, piping design, and controls have a pretty major impact. And if we're looking at the grid, even the pumping can have a big impact. So let's get an A on our design.
You're good. You're live.
Great. Thank you so much, Jeff. So we have some time for questions from the audience. So take a few questions if anybody has them now.
Jens Ponikau, NY-GEO. Jeff, congratulations, you hit the point here. Keep one thing also in mind when it comes to pumping power. Every single family building I've seen here in New York State, even the ones in Buffalo, New York, are cooling dominated. And all that pumping power, that means we inject more heat into the loop field than we're pulling out. That means the cooling load is, even if we're cooling the building with domestic hot water production during the summer, or at least the loop we're cooling. And all that heat ends up in the loop field. Heat is the enemy because the design for the loop field is driven by the cooling load because it's the dominant load. So yes, you're saving $5,000 on a pump and you put a big, very inefficient pump in there, but it's going to cost you 2 or 3 boreholes at $50,000.
It's a really good point, Jens. Not to mention that higher loop temperature is going to increase demand. So it's definitely building on it. Yeah, great point. Thank you.
Thank you. Anybody else have a question for Mr. Hammond? All righty. Thank you so much.
Thank you.
Appreciate your presentation. Well, next up, welcome Tim up to the stage.
All right, thank you. How's everybody on day 2?
Great.
All right. How about shaking this up a little bit with the Q&A happening in between? I like that. Good job, Mitch. Good job. All right. John Ciovacco had given me a call and said, let's just talk about auxiliary heat versus backup heat. So you're going to see the theme here. As Jeff was just referring to pumping, we start to look at auxiliary heat. We start to look at backup heat. You're going to see what the other two are going to bring. So first of all, thank you for taking time and being with us here this afternoon. Very, very much appreciate it. So I'm going to jump in here. The power of communication. You're the voice of reason. You are the ones helping to make the right choice, obviously impacting many for multiple decades. Your guidance matters. I want you to really think about that, please, for a minute. As Jeff was just referring to that bad pumping, the nightmare pumping situation, that one decision or the one part, the power of communication, it wasn't good. It didn't happen. How do we make sure that we at the table are in full communication with all parties involved? I really want you to, whether you're here residentially or whether you're here commercially, institutional, I want you to think about the power of your influence, the power of your communication, and what impact do you play? What role do you play to make sure that this is a very good product at the end of the day? So I do want you to think about that. So the one thing, and I know I'm just kind of playing with this, but I still feel like we're in a little bit of rural New York, and I like that because my belt and suspenders, hopefully that resonates with some people. You may not have seen belts and suspenders out in the real world lately. People are laughing. That's good. That's good. We're here to have fun. My point is there's a lot of things that happen with a system where you can have the belt and suspenders approach. But sometime belt and suspenders, if you take a look at this, what does it imply? Multiple conservative approaches for redundancy. Let's be careful on that. So here as we talk about auxiliary heat, And here, as we talk about backup heat, again, Bob did a beautiful job in the presentation just before this on really understanding if we have a geothermal heat pump or a water source heat pump that can do the work, and if you saw the efficiencies at worst case conditions, you still have geothermal in the range of 3 to 4 COP, an extremely high EER. Why would you not want that compared to a COP of 1? So again, the belt and suspenders, I want you to give this consideration. I'm going back to the communication standpoint. And we have talked over the past day and a half, whether it is one system, whether it's 500 systems, or whether you're building a development. Does this decision right here matter? If you're looking at a development, you bet it does. That one decision matters. What if somebody goes in and belt and suspenders and said, I want a 15 or 20 kW backup heat on that 2-ton heat pump? Does that really make sense? Number one, no. It just does not. So we have to be reasonable. We have to be respectful for what we're doing. I wanted to throw this in because I think everybody at this conference understands what's at stake. And again, back to the communication. Yes, it's one conversation that you're having, whether it's at the kitchen table or whether it's in a boardroom. Please understand, since 1949, we see the trending of what's happening with electricity. You've obviously got 3 different groups of people here that are proposing that it could go a little different direction. However, do any of those propose that we're going to use less electricity in the future? The answer is no. Whether it's electric vehicles, whether it's data centers, solar, on and on and on, we are going to continue to consume more electricity. So this has impacted upon us. There's been a couple references today from multiple different speakers, but I know one of the references even that John had made earlier, and I'm back to this, whether it's 1 unit or whether it's 1,000, we have to consider the impact of what we're going to do to the electric grid. Back to the communication is we need to make sure that we're lock in step with the utility to make sure that we understand what that consumer is truly looking for. So when you take a look at system design, sizing matters. Jeff just carried a beautiful little example of how it can be done correctly. And I don't want you to focus here so much on all the numbers at the bottom. They're as a point of reference for you, but I want to just give perspective. And again, it was covered in multiple sessions. We need to make sure that this system is sized and designed to handle 100% of the load. And I think, again, NYSERDA Clean Heat Program dictates that. And I think that's a wonderful thing, all right? However, you've also got, and I'm talking to the rest of the country, as well as maybe even some other markets, you have areas in the country that only demand that you size to 80%, 90%. I want you to take the same methodology, though. Are we more efficient with geothermal versus 1.0 COP of auxiliary or emergency backup? Again, everything that you see at 32-degree entering water with geothermal systems, your COPs are in the range of 3.5 to 5, depending on manufacturer. So just incredible opportunities here. So the reason that I also highlighted this at the bottom is, again, you've got a contractor, or maybe you've got a specifying engineer if we're talking about a commercial opportunity. You've also got the utility involved. You have a homeowner or a building owner involved. All of that plays into what's the size of the system going to be and what's the performance going to be, so that you all know that, and all the manufacturers represented, we have that software to help you, whether it's residentially or commercially, or your design engineers across the room can help you as well. So impacts to consider. Again, whether you're a homeowner or builder, guide them from misinformation. Is there any misinformation out there in the marketplace today? Everything on the internet true? We all know better. We really have to make sure that we don't just jump on to the misinformation, but actually focus on what's true. What does the data say? What do the studies say? So again, we have a more informed buyer. Make sure that people understand the truth about air source heat pumps, cold climate heat pumps. Where does geothermal fit in that spectrum? Balance point. I know sometimes we get too nerdy on this stuff. Balance point matters. Let's really understand at what point does the GEO system, is it not able to carry the balance or the difference? We need to be able to know that and share that and communicate that. Obviously, smart controls. So I'm back on my little kick here on auxiliary versus emergency heat. You're going to find in a lot of most commercial applications, there's no backup electric heat systems in each of the distributed heat pumps. We're also going to see a trend, in my opinion, on thermal energy networks, systems, geothermal systems installed, potentially no backup, no auxiliary. Jens just pointed out summer peaking. Is it really that big of a deal? So I'm just challenging this group to pay attention to their design practice and their design principle. Is what is necessary, what is required. If you're the contractor, I want you to really be thinking about sharing all the options, making sure they understand the options. The last thing you want from a building owner or from a homeowner is to say, I didn't know that option was available. Why didn't you share that with me? And I'm probably preaching to the choir, but so many times geothermal is not even brought up in the conversation. So we have to be the ones to present that. We have to be the ones to present the correct information. And again, electrical service implications. Go back to if you want the belt and suspenders approach, 15 or 20 kW heat. Is that really going to help the electrical service? Not at all. Multiple systems. I've discussed this with numerous people across the country. For those of you doing residential, doing homes, 3, 4, 5, 10 units, there's a lot of contractors that are now saying they are picking and choosing which systems they put auxiliary or backup heat into. Interesting thought, interesting design principle. Because again, with everybody having smart controls, the contractor, the homeowner can be notified immediately if there's a problem with a heat pump. We don't always have to have a crazy amount of kW backup. The other thing again, and I've covered this earlier, I want you to give this consideration of it's not just your choice. It's what's happening on the electric grid today to make sure that we're leaving room for others, knowing electrical demand is going to pick up. And again, the other thing that I love is we have so many utilities now that have joined us here at NY-GEO over the years. We need to also view this through their eyes. We need to understand what's important to them. That's critical to make sure that they're at the table with us from a design principle. Again, I've covered the other portions of that. The last one I would say is consistent load, low and predictable kW demand. That's the benefit of geothermal. That's what you'll get in the summer. That's what you'll also get in the wintertime when it really matters. So there's my contact information. Mitch, I'll turn it back to you.
Absolutely. Thank you. Thank you, sir. Appreciate the presentation. So now we've heard pumping considerations, auxiliary heat. There's got to be some kind of energy in the audience. I know somebody's got a question. Who has questions for Tim? Don't all jump at once.
Thank
All
you.
right.
There'll
Thank
be
you
more
so
time
much,
at the end. Yep.
Here, which is when you do job, you know, you love it, and it's just so happens to job. Put train in practice. And it's for you.
Wow. Ground source heat pump shave peak load. We hear it every day. Everybody talks about it all the time. Bob Brown did a tremendous job in the last hour talking about the different technologies and how they stack up against each other. That was decades of experience. If you weren't here, you should watch that video of that presentation. and standing on the shoulders of giants, Bob in particular, to set some context, about 15 years ago, maybe more, Bob can tell you more, he started thinking about how do we prove this? We study after study after study. Let's just prove this once and for all. And he and his engineering team developed something called Aurora Controls with Symphony interface to spit out some of the data, what these products were actually doing. So we're celebrating the 10th anniversary of the launch of Symphony this year, which is a system that collects over 100 data points on over 15,000 individual heat pumps across the United States every 10 seconds. So since I've been talking, we've collected over 1 terabyte of data. And we store that data and we use it to do what Bob originally intended, I think, is troubleshooting, predictive analysis. Somebody in Des Moines, Iowa needs to change their filter because their suction pressure's gone way up. We know that stuff and we share that, and that's terrific. But we've taken that system to the next level and started looking at what are the grid impacts of these heat pumps. They knocked my name right off the podium. What does that actually do? How much is it? We have these theoretical numbers. We have all kinds of guesses. But now we actually know what it really works out to. Simply stated, this is what we're talking about every day, is a furnace and an air conditioner, or excuse me, a heat pump and an air handler with electric strip heat does this to the grid. It peaks it out. If perhaps you add a geothermal unit with auxiliary heat, it's less, but it still can kick on strip heat that Tim was just talking about. Ground source heat pump without strip heat is the grid's best friend. And a lot of us are thinking, but you always put strip heat in a ground source heat pump and it always operates every winter. Surprisingly, that's not what the data says. It's quite different. And we're going to take a look. So as a director of utility engagement at WaterFurnace, I answer a lot of questions from utilities and public service commissions and things. Like, we see the theoretical studies, we hear this stuff, we see the ratings, but we don't really believe it. Show me. I want to see the data. So one of the folks I've been working with is Great River Energy in Minnesota. They said, tell me about some temperature bins. I want to look at 15 to 20 below zero, 10 to 15 below zero, 5 below to 0, and then, show me what the performance was of all the heat pumps in Minnesota in a specific location. They gave me Windham, Minnesota on January 15th of last year. So I pulled up all the heat pumps. You can see the dots on those maps represent the kilowatts per nominal ton. So if it's a 5-ton heat pump, the kilowatts used are per ton in the 5-ton heat pump. That's kind of interesting because back in the day when a single-speed system was the rule, then a 5-ton heat pump always was a 5-ton heat pump. But now sometimes they're 2-ton heat pumps or 4-ton heat pumps. And you can see that the actual kilowatts used per ton are right there around 0.6 at 15 to 20 below zero. Well, what does that mean? Well, if you take those 360 readings over that 1 hour of peak load at the Great River Energy grid in Windham, Minnesota, those 23 systems averaging 3.4 tons capacity performed at an average COP of 5.33. None of them used electric auxiliary heat between 15 and 20 below zero. In fact, none of the heat pumps that you're looking at here used any electric auxiliary heat at any time during that peak load time. Then again, the same is true. And as you see the temperature creep up towards zero and get warmer and warmer, the COPs creep up to 6.6 kilowatts per ton. Again, that's 360 readings, 10 seconds between each reading for an hour of peak. That's not an ASHRAE standard. That's not an AHRI measurement. Average COP is not a thing yet, but this is what the utility company specifically asked for, And that's the data that we provided them. And then the phone started ringing. Everybody wanted to see data like this. So they gave me 5 locations and 6 peak events, 3 summer, 3 winter peak events. We said, okay, we'll plot those and see what happens. And you can see the number of dots represents the heat pumps that are in that area, that specific location. Duluth, Fargo, if you can't see it, Minneapolis, Sioux Falls, and St. Cloud. And the first 3 peaks are heating. So they're all January 15th, February 28th, and December 18th, all in 2024. And those heat pumps are operating at COPs without electric strip heat ever being activated at that peak load event, around 7 COP. That's the actual performance of those heat pumps taken over that hour. In the cooling event in the summer, you can see that the average performance in those same locations of those same heat pumps was about 36 EER. Now, of course, they're not rated at 36. Most of them are in the 20s, maybe 30, but that is what they actually did for that heating hour in those 3 cooling events in 2024. That was kind of interesting. So, of course, the next question they said, well, what was the weather? And so, we go on, and these studies kind of continue on. But what we find is in Texas, in Austin, Texas, the Public Service Commission and a local utility said, well, what happens when it's really hot in Texas? Really, really hot. This is Austin. You can see 4 date time groups there in 2023, in June, July, August, and the last one's in September. And the temperatures are right there, 99, 103, 106, and 106, I think. That was a hot day in Austin. And those heat pumps, over 50 of them operated at those EERs that you see right there. Now remember, you may or may not know this, but if you have a lot of time to dig through the AHRI database, you'll find that the top performing air source heat pump on the planet at 5 tons has an EER of 13 at 95 degrees Fahrenheit. So plug in that 106 and it's much lower than that. That's the best performing air source heat pump in the world at 95 Fahrenheit. And at 106, we're hitting 25 EER steadily for that entire 1 hour peak event. That's just the data. It's just what it says. Not cherry picking. We did eliminate all the heat pumps that were turned off. We eliminated the ones that had no change in water temperature. I used a minimum water temperature change in the loop of several degrees, and so on and so forth. So this is not cherry picking. These are real working full capacity heat pumps in Austin, Texas. And then the folks in Ontario asked the same question. Well, what happens in the summertime when they're still a summer peaking utility? Well, ground temperature there is pretty low in Ontario, and we hit 44 and 48 EER during their 2 peak events. You can see it was 118 units in the first sample and 155 in the second. And again, we filtered out the non-functioning systems. Strangely enough, there were several heat pumps in Ontario during those peaking events in the summer where they were actually in cooling mode. Who knows what they were doing? Maybe they were in a wine cellar or something. But these are all the operating heat pumps during their summer peak events. 28C, anybody want to do the math? 86 degrees roughly, ballpark. And then again, in Indiana, where we manufacture these heat pumps, you can see similar results, 48, 36, 36 EER. This is not like your run-of-the-mill summer day or your run-of-the-mill winter day. These are the highest peak events on those respective grids throughout the entire year. And these are the actual performances that we measured. 7.8 COP, 7.2, ridiculously high actual COPs. I threw in some air source heat pump comparisons there in the blue just to get a feel for what we're talking about here. I was staggered when I saw this data, but there it is. Again, here in Maryland, we had some questions from the Public Service Commission there, and these are the answers that we came up with. This one here, you can see in Maryland on the left, there are 700 systems averaging 3.8 tons. None of those systems used electric strip heat at all during this heating peak event, January 22nd at 7 a.m. last year. At that same time, there were just 61 systems in the state of Maryland that had auxiliary heat activated. That's 11 to 1 is the ratio. Well, a 10 to 1 ballpark. But even using auxiliary heat, those systems were operating at COP of 2 in their kilowatts per ton performance. So in the cooling mode, of course, we did real well on the right there with the EERs extremely high, using just over 0.4 kilowatts per ton and showing a average cooling EER in Maryland of 27.3. So, wow, it's not just, in Indiana, and it's not just in California, it's across the map we're finding these results. Okay, I've got to wrap up real quick here, and I can't see. Okay, sorry, little animation taking up time. And New York, let's finish up with New York. Take a quick look. Again, 93, 84, 93, not the hottest days of the summer, but the biggest peaks on the grid. And again, in the wintertime, not the coldest days, but the biggest peak time on the grid. Some utilities want to look at temperature bins, and some utilities want to look at peak events. But in New York, we looked at 3 locations you can see on the map. We used upstate, Rochester, and New York City, and those were the respective performances at that peak event, 5 p.m. on July 28th last year, 2 years ago. And then last year, the peak event was January 1st. Just ridiculously high performance. Some of that is the practices in this area on this map. The practices that the installers use here and the drillers are significantly, measurably better than in some other parts of the country. The training's high, performance is high, the units perform better. So that's all I've got. I'm going to wrap up there. Sorry, went a little over, but
Great. Thank you so much. Appreciate the presentation. I've got time if anybody has one for maybe one quick question. We got one over here. Go back. Stay here.
thought I was going to get out of there. Yes, sir.
Great presentation, Mr. Lange. Here's a thought. So you were showing spot historical performances, which are never an indicator of future performance. So do you whip out the old farmer's almanac to really get some historical perspective in regards to what could be the worst, hottest day, cold day, and throw that into a model to get a better indicator of future performance?
Yeah, we do that. I use Weather Underground for historical data. Nobody knows what's going to happen next, but the very first slide was actually bin data at specific temperatures in Minnesota. We did the 20 below 0, 15, 10, 5. And yeah, you can pretty well predict how that unit's going to perform next winter when it's 20 below 0 based on what it did last year. Something Bob pointed out in the last presentation you were here for is that these units don't really degrade in performance over time because they're not exposed to outdoor fouling and so on. So yeah, we expect that they're going to perform that good for the next 20 years. That well, excuse me.
All right. Thank you so much. Up next, we'll have our final panel presentation from Mr. Max Ciovacco.
Thanks.
Hello, everybody. I just want to say thanks for having me here, and I'm honored to be sharing the stage with these industry giants over here. I'm Max Ciovacco. I may or may not be related to John Ciovacco, depending on what he says. I'm a project manager at NYSERDA, and I'm here to talk to you about smart panels. So, what is a smart panel?
So take the input.
Okay, okay. I was going to say, we have the wrong slides. Anyway. What is a smart panel? So a smart panel is a internet-connected, software-controlled circuit breaker panel where each circuit has a current sensor and a relay built into each circuit breaker. So at a high level, each current transformer allows the system to know exactly how much electricity goes through each circuit. And with that information, we're able to know we're able to determine how much power each circuit uses with the software, and you can control when a particular circuit is allowed to draw that power at any time that you specify. So with the smart panel, we can address some existing service limitations. Currently, 80% of electric home peak events are around 12 minutes or under. So shifting the operation of just one load can mitigate 90% of peak events. So with that, a smart panel can actually reduce or completely avoid a panel upgrade. And you can leverage the IRA $600 tax credit to reduce some of that cost. So one of the barriers that we run into in New York is most of these homes are going to need a 200 amp service panel. 75% of existing panel capacity in homes is not adequate for the current technologies we have available for these homes. You really mess with my slides, man. Upgrading to a 200 amp panel can cost anywhere between $1,500 and $3,000, but that's only if the street lines are adequate enough to handle the 200 amp service panel. If they are inadequate, it can cost upwards of $10,000 and above to upgrade those lines. So as you can see here in some of these charts, we have some examples of electric loads, and the stove, hot water heater, and heat pump alone can go over the typical 100 amp service panel. And then you can see some of the vintages we have of electrical services. So 41% of houses before 1950 will need an upgrade is pretty significant. Essentially, millions of homes in New York are not adequate and will need some sort of panel upgrade in order to handle these new technologies. So at NYSERDA, we do have some initiatives to help mitigate the costs of these panel upgrades. One of them that I'm going to highlight is the Enabling Innovative Clean Energy Building Solutions, or PON 5982. Essentially, this this solicitation anticipates making 5 $1 million awards to the following topic areas: building envelope, clean heating and cooling, integrated grid interactive building controls, smart panels, low GWP refrigerant applications, and leak detection and thermal storage. And I was very brief. Thank you very much.
Nice. Thank you, Max.
Skip. Switch. No questions, I guess.
You can start. Well, so now we're going to open the floor for questions for the entire panel. Hoping everybody has built up all of their questions and they're all primed and ready to go for now. So who's up first? We got a couple in the back.
You go. You challenge this time. It's very much you.
Thanks. Steve Martino, CDM Smith. Question for Max. That panel you just showed, can you buy those breakers and just put them in the panel you already have? Or do you have to buy the entire panel?
You have to buy the entire panel. They're not just one breaker that you can throw into an existing panel. So
Okay.
You will have to upgrade to an entirely smart panel.
All right. Thank you.
Another one up front.
Sure.
Hello, sorry.
Take it away.
I'm Lacey from the NYSERDA Regional Clean Energy Hubs, or Energy Smart CNY. I have a question for Tim. As an energy advisor, I'm commonly talking to a lot of different customers and trying to educate them on the different technologies and programs. And what do you recommend when educating customers about ground source versus air source and auxiliary versus emergency? What do you think is the most important thing to explain in order for them to make an informed decision?
Wow, awesome. First of all, thank you for what you're doing. We appreciate that. Again, back to a comment that I made earlier just on misinformation. I would absolutely just stick to studies that you can, as Will said, or even from the standpoint of actual data. So request that they speak to, number one, an IGSHPA contractor that's been IGSHPA certified for training to install the ground loop, and make sure that they have that. I would also make sure that you ask for a list of references so that you know how many systems, or a consumer knows how many systems somebody's put in, so it's not their first. And then I would absolutely, again, make sure that you're dealing with somebody that is reputable, a reputable contractor, good reviews. And again, on the auxiliary side of that question, again, you're going to definitely head toward a geothermal heating and cooling contractor that has great experience. They're going to look at that panel. They're going to be able to do a heat loss, heat gain calculation and determine what the BTU requirement for the heating and cooling truly needs to be for the home, size the system appropriately, and then specifically give that homeowner the data on how much auxiliary heat is going to be required. What balance point did you size my system for? I think that is a key question that a homeowner or somebody should want to know, is how did you determine the size of my system? And then I think through that bin data, through the data that Will was also able to highlight and show, it will tell you how much of the heating and cooling will be covered by the geothermal versus is there auxiliary heat going to be required? And if so, how much? And all of those are typically broken down in what they call bin hours. How many hours per year are at a certain temperature? So make sure that you're trying to find, or encourage them to find, a contractor that understands all that and that also truly does geothermal. Because many will indicate that they do, and they will try to talk that homeowner out of it immediately and not discuss it, and then just sell their cold climate heat pump. So, Will, any comments on that?
Talbot.
I want to see the loop design. Show me the loop design. Software. Not this loop design, the software.
Question there?
Yeah, Dan Robb at Frontier Energy. Questions for you, Will. Looking at some of the COP data from the downstate New York showed pushing 18, and want to say amazing, but it almost seems too good to be true compared to some of the upstate region. Could it be a data anomaly, or did you dive into some of the causes driving such high COP in that area?
Yeah, it was higher than that. I eliminated dozens and dozens of heat pumps from that study that were not actually even turned on. Maybe they were summer homes or winter homes or something. It's high, but if the unit is operating, that's the beauty of a variable speed or a two-stage system, is a 5-ton system doesn't have to be running at 5 tons. It could be 2 tons. And then it's only using a fraction of the energy at that peak event. The other thing was that downstate peak was not an extreme weather event. So the heat pumps weren't really taxed. The grid was taxed. Don't know what was going on. Maybe everybody was watching TV at the same time. I don't know. But the weather at that point in time was not extreme, so that COP didn't seem ridiculous. I mean, it is ridiculous, but in the realm of geothermal, it was just good.
Good.
Thanks.
Alrighty, any other questions in the room? One in the back there.
Peak.
Yeah, Jason Hertzen, Durant Energy. How do we use all this data you presented to talk to the utilities to maybe give them an incentive to lower electricity rates for ground source? I think this morning John Thomas talked about that happening. I'm just curious if that's a thought here.
So
that's literally my job. And I've been doing that a lot in Minnesota lately, other places, Maryland Public Service Commission last week, Virginia yesterday. If there is an individual, the problem with utilities is that there are thousands of people in silos. Who do you talk to? So if you know the guy or the gal and you want to engage, any one of us would be good at talking to them about that. And I can bring whatever I've got to help to that conversation.
Anyone else from the panel? Thoughts on that subject?
I would just add on to that. I think the term friendly competitors, we both manufacture geothermal equipment. We've got another one here in the front row with Climate Master. We're all in this to win it together. So even if it were to be somebody from our company, from Climate Master, from Bosch, from WaterFurnace, bring them all in together. Feel free to do that. We welcome that all the time.
Not a question, but I just wanted to mention that Con Edison does have the select pricing plan. It is not a geo-specific rate, but it is very beneficial for geo customers. The current data available says about 10% savings, so this is a demand-based rate instead of consumption. So we have flyers at the Con Edison table. Come see me downstairs. I can tell you more about it.
Another quick add that I would offer is, in many cases, utilities are great sources, in some cases allies, but ultimately they all are obligated to listen to regulators, right? So if you find whoever the regulatory body is, having a conversation with those folks on driving rate reform is very important. I'm sure almost everybody on the stage has had those discussions already. Any other questions?
State your name. Thank you.
Thank you. Dan Silvestri, I'm an installer. I think this electrification is starting to change the way we are sizing our equipment to the loads now. Years ago, it was single stage. And then you want us to supplement it with electric or whatever. Then we went to two stage to size it for the heating side, and then so you wouldn't have comfort issues on the cooling. Now, I agree with 100% geothermal sizing to that, and now you're not talking any supplement or emergency. I see it as a contractor that if we don't have emergency backup, because of supply and demand of a lot of parts, I can't tell my customer I got to wait 2 weeks, 2 months for parts. So I would be inclined to put in emergency backup, and we can have a switch should, God forbid, we lose a compressor or this or the other thing, or a blower motor. So I don't know where this is going. I see an evolution here, and it's a little scary on our end because we're on a fire line with the customers. But I understand the utilities have issues because of this electrification. So what's the happiness on here?
Dan, that's a great question. If everybody didn't hear that, it's should we even put this in? You know, you don't want the phone to ring, right? You don't want to, like, I'm cold. So that's the difference between auxiliary heat and emergency heat. You put in emergency heat, or do you put in auxiliary heat because you short looped it? So it's really a value decision between you and the customer, and maybe at some point the utility company may have something to do with it. There are many utility programs, several that I know of, that eliminate electric heat as an option if they're to qualify, the customer wants to qualify for an incentive. So that's an emerging trend as well. Now, again, but as Tim was talking, auxiliary heat, emergency heat, big difference. Same stuff, big difference.
Yeah, I'm talking about emergency heat right now.
Yep.
But the other thing is, I have a situation in a city that I have natural gas. It's right in the building, and the city will not allow me to tie into that natural gas. So I wanted to do a geothermal with gas backup, and I can't do that. I mean, it's great.
Yep. Do you want us to argue with the fact that you said it was crazy right now? We're not going to do it.
Who else? Anyone?
I will add on to that emergency backup heat isn't just for electrified homes. If you have a home that's on a oil boiler, and that boiler goes down, they have nothing. They have no backup either. So it's not just for electrified homes that have that issue, but it's an issue for pretty much any HVAC contractor around the country.
Bob.
All right, if none others, I have one to throw out. So we heard about each of the components that makes these systems in design, in modeling efforts. How can we put forth our best foot forward at the component level, right? And we heard, how do you have the crystal ball, and how do you look to the future? What role do you folks on the panel feel overall system controls and monitoring play in the overall optimization of system efficiencies and achieving this reduction of grid impacts? Anyone?
Take a quick swing. We were concerned for several years that by collecting Symphony data that we have on these thousands of units, that it might not turn out so great. Let's hope it does. Turned out far better than expected. That's don't know what effect that is going to have on the future, but I will tell you that there are brands in the air source heat pump industry that are collecting about the same amount of data we are. They won't share it. And I know the engineers that designed that equipment and look at the data, and it is a secret. So we're open kimono here. We show you what we've got. And in fact, something most of you don't know is Hugh Henderson. I don't think he's here still, but he did the foundational study for clean heat, actually using 52 systems with that data, and established the baseline COP for ground source heat pumps. And from that, years ago, we now have this giant conference and clean heat to show for it.
Thank you, Mitch. Great question. I would just indicate from our vantage point, the past few years, we have tried to make sure that communicating controls was an option, was available for all of our equipment, regardless of what model. So we truly believe communicating controls, alerting the homeowner, alerting the contractor, building owner, whoever that is. So that is certainly something that we see. That trend is going to continue. The other thing that certainly we're heading toward is variable speed. We showcase that in our display yesterday and today, and we truly believe variable speed, whether it's variable speed pumps, whether it's variable speed ECM fan, compressor, we truly believe that is the future of where we're heading. Again, multiple reasons why. Obviously, electrical consumption, but also being able to vary the load depending on what that temperature truly is, heating or cooling, to lock that in for optimal performance and comfort.
Anything else? Two of you? Yeah. Jeff, Max, nothing? Okay.
Anybody hungry?
Other questions? All righty. One more time. Oh, hold on. What about building automation systems? I think we got a little bit of a touch on that. It was the last one.
Sure. I especially on commercial buildings, building automation systems really give us a lot of data, and it kind of builds on what Will and Tim mentioned for their systems. That's something that is really important, and how we can measure how the systems are operating, number one, but also it helps us with scheduling, if we're looking at peak demand, if there are utility programs, whatever that might be. The big advantage of ground source equipment, especially if we're talking about unitary equipment, multiple packaged units throughout the building, is you have that diversity of load, but also you have all that piping that's interconnecting. So if you have units that are heating and units that are cooling at the same time, you're just moving heat around. You're not really even taxing that ground heat exchanger, and the building automation controls are going to help make that all work together, because we want the pumps to vary, we want the heat pumps to turn on and off, we want the whole building to act as a integral system. And I would say, any commercial application that's at least 50 tons or so should have some sort of DDC controls in order to help make all that work together, in my opinion.
And you work cell managed system pump, and then recommend that if they don't have a built-in automation system, they should consider that.
Well, as far as I know, all the heat pump manufacturers have controls available for their heat pumps. So you would typically ship that heat pump with, let's say, a backnet controller, and then that backnet controller would be on the building network with a front end. So you would have to integrate some controls. You'd have to have a controls contractor involved, but the heat pump itself can talk to those controls. But sure.
All right, one more time. Thanks everybody on the panel.
Thanks, Benji.
Great job, guys.